Good afternoon, everyone, and welcome to the IMechE Tech Talk for September. This is from the Teesside Committee, IMechE, in the North East of England. My name's Alan D'Ambrosio. I'm work for ABB, but I'm also on the IMechE Process Industries Board as well. So, just move on to the next slide. I'm delighted at this Tech Talk to introduce two speakers, David Burgess from ABB. David's a fellow at the Institute of Mechanical Engineers and a principal consultant at ABB, and he's going to be talking about transitioning from intrusive to non-intrusive technologies around inspection. And then he'll be followed by Dr. Praful Sharma from CorrosionRADAR. He's the Chief Technology Officer in CorrosionRADAR, and he's going to talk about technology that we can actually use, predictive corrosion monitoring technology for corrosion under insulation. So I think there'll be two really good presentations. We'll have a poll within their presentations and an opportunity for you to question the speakers as we go at the end of the presentation. So if you've got any questions, please feel free to send the questions in there, and I'll pick those up at the end. Okay, so, and this is the future topics we've got with the IMechE. So you can see a number of YouTube videos where you can actually see the IMechE in there. We have our annual general meeting of the Teesside Committee on the 15th of September and a North East Regional annual general meeting as well as on the 17th of September. And the PVP number get professionally registered on the 22nd of September. So future catch-ups and meetings where you can see the IMechE. And some of the future topics as well on there. So, and at the end, if anyone wants to look for any additional topics, please feel free to either email myself or you can see Andy Stevenson, the Teesside Chair's email address as well, with any future topics on there. Okay, so with that, I'll hand over to our first speaker, David Burgess. So David, if I can hand it across to yourself, and David will take us through the transitioning from intrusive to non-intrusive inspection technologies and how you can work that in your site or plants.
Okay, thank you, Alan. And good afternoon, everybody. As Alan said, my name is David Burgess. My role within ABB is I work for the inspection department. We carry out inspection for in-service pressure equipment. So this is inspection of not new equipment that's been made in factories, but for sort of equipment that's in service. My role really is to support the engineers and clients, my engineers and clients out on site. I also do risk-based inspection. We have software for that, which is relevant to this topic. And I'm also responsible for all of our processes and technical procedures. Okay, so I've been around the industry for some 40 years now. Started as an apprentice with ICI, for those of you that might remember that, and worked for INEOS. Came to ABB 12 years ago as just a change of role, really. I've been working with inspection ever since. Much of this topic really is just, we're starting to see this more and more now. Traditionally, inspection of in-service pressure equipment was done invasively internally. So you'll see that typically a pressure vessel would look like that on the right, and you would normally go inside by a manway, which you can't see there. It's probably on the other side. So we're going to look at exploring how you would go about inspecting that vessel without going inside the vessel. Okay, so just the agenda there. What is non-intrusive inspection? What are the objectives of it? It might seem obvious, but there's some not so obvious reasons. What are the benefits? What are the challenges? There are some historical challenges around that. And then what the methodology is for that, you know, how and such, what's the right way to go about it. So we'll spend some time on that. And then some examples of non-destructive testing that will support non-intrusive inspection, a couple of case studies, and then a summary. And as Alan's really said, I've got a couple of poll questions, so please answer those when they come along with the slides. So I'll be talking for about 20 minutes. Right, so let's make a start. So what is non-intrusive inspection? Well, pressure vessels often contain high hazard substances with significant stored pressure energy. Flammables, toxic, compressed gas. So it's very important to understand the condition as it goes through its service life. Some of these vessels can be, in excess of 30, 40 years old, and they can be carbon steel, and the paint system can break down. They can corrode internally, they can corrode externally. Very many damage mechanisms that can be relevant to these. This will be a typical pressure vessel in service. So you can see they tend to be cylindrical in nature to contain the pressure. They have ends. In this case, it's got a manway there to allow internal access. And you can see it's connected to pipe work, some structure around it, some drain pipe work, instrument tappings and such. So that's a typical sort of pressure vessel. From internal deterioration mechanisms would be things like corrosion, cracking, and they're likely to have severe consequences if they got to a state where the pressure overcame the corrosion or any cracking in there. So as such, pressure vessels are required to undergo statutory periodic inspection and other non-destructive testing to ensure that they're continued safe and reliable operation. So things like in the UK, the pressure system safety regulations, provision and use of work equipment regulations, these are the conduct control of major action hazard. These are the regulations that ensure that pressure vessels on this sort of duty are inspected on a routine basis. Similarly abroad, they have some of the regulations, but they are different, which we'll talk a little about later. Now, traditionally, this has meant internal visual inspection, abbreviated that as IVI, and then supported by any non-destructive testing. That might be crack detection, thickness testing of the shell, that sort of thing. Now, non-intrusive inspection, and abbreviated that as NII, is where the internal aspect of periodic inspection can be carried out from the outside of the vessel, often without taking it offline. So when it's actually in service online with the process, the fluids in there. So therefore you don't need to open it for cleaning and manning and such. The development of advanced NDT techniques and assessment methodologies has allowed this to become accepted as a safe and alternative option, of course, where the right circumstances allow. So that's what NII is, and that's what we're going to talk about. Next slide is coming through now. So what do we think the objectives are? Well, the obvious one is overall cost reduction, and that would be the cost saving of not having to isolate, empty, prepare, clean the vessel for man-entry. So there's a large saving in that. And then also, you may be able to keep the item online in service, and therefore you've got increased uptime. So, of course, there's a saving in that, in that you've got increased production. Less interruption to production. But there are other objectives as well. You might want to do it, for instance, to support deferment of an internal inspection. So let's say typical frequency for that sort of vessel might be 4 years. And let's say for some reason you need to extend it by 1 year. Then you might do an external non-invasive inspection to support that. Another reason might be to complement an internal inspection regime. So you might say, well, let's inspect internally every 8 years, but let's do an intermediate non-invasive one at 4 years. So that might be a strategy that you use for non-invasive inspection. You might have an unscheduled inspection due to operational excursions. So you might have seen that there was particularly high temperature or perhaps high pH in the process fluid, that you've got concerns about corrosion. So to avoid bringing the plant offline, you could do a non-invasive inspection there. So that might be another reason. And the other reasons as well are to minimise disturbances to vessels which could create problems. So, for instance, when certain vessels, if you let moisture in, it can react with the residues of chemicals in there and cause further corrosion. So you might want to prevent that. There might be undesirable odours. We have clients that really don't want to open vessels up because it creates a smell and potential sort of environment industry. So you might want to do it for that reason, or all the other reasons such as pressure. Vessels that when you bring them offline and then bring them back up to pressure, you're introducing pressure and thermal cycles, and some equipment is more sensitive to it than that, so you would prevent introducing that as well. So you can see there are a number of objectives that that you might lead you to non-invasive inspection. Just to say that the inspection requirements should be defined such that the risk levels are not increased. This effectively means that there should not be an increase in the probability of failure when non-invasive is used. So that's a whole point of the methodology, really. If you're going to do non-intrusive inspection, there should not be an increased risk, and that's that. Okay, so what do we think the benefits are of non-invasive inspection? So apart from the obvious cost saving that we've just discussed, it avoids personal access, which can be hazardous. So in the UK, there's a confined space entry regulations, and like with most safety risk assessment, it talks about removing the hazards, not putting yourself at harm. So non-intrusive inspection actually achieves this. It says, well, it's a way of not going in a confined space. So there's certainly a benefit. You can, another option is planning for turnarounds, shutdowns. If you do the inspection before the turnaround, if there are any defects, then it allows you to plan for that remedial work in the turnaround. Whereas if the inspection was done in the turnaround, you might not have time to order the materials and do any repairs. So there's definite benefit there. Obviously, if there's less vessels to open and inspect in the turnaround, then you can shorten the turnaround duration. It reduces the environmental impact. When you're cleaning out vessels with contaminants, then there's less disposal. And it avoids potential damage to internal components. So you might have, for instance, expensive catalysts, packing, lining, coating, refractory. If you don't have to go inside, then you won't damage or deteriorate that. So there are certainly some benefits there. So I'm going to ask you a poll question now. So can you launch the poll question, Fiona, please? Let's see how this works. This is our first poll question. Fiona? Hello?
I can hear you, Dave. That's fine, but I can't see the poll questions coming up.
Yeah, okay. So I don't think the poll question's coming through. So let's move on then, and then we'll see the next poll question. Okay. If it comes up, then we'll take it when they do it. So what are the limitations of non-intrusive inspection? So you can't do it to every bit of kit. So there are certain circumstances where it might not be appropriate. So if you have a lack of understanding of the operating regime, where you don't fully understand what damage mechanisms there are and such, then you can't really go down that route. Or if you've got a lack of understanding of the potential deterioration mechanisms, rates the same. If you've got high severity and rate of degradation mechanisms, so if you know that there's high corrosion and excessive rates, then it's probably not appropriate. If you don't have any inspection history, if you don't know enough about the item to know that the last inspection it was good, or a vessel of the same or similar duty, then again it's not appropriate. If the item's close to the end of life, so I mentioned before, some of these vessels can be 40, 50-year-old, then there may be numerous defects close to the minimum thickness, so probably not appropriate there. And where there are damage mechanisms that can't be detected or monitored from the outside of the vessel, maybe due to the vessel geometry, then again not appropriate. There may be extensive manufacturing defects that are really hard to monitor from the outside. And it's what I talked about before. There may be national regulations. In the UK, the pressure systems regulations are reasonably flexible and they allow you to apply this methodology. In some countries in Europe, it's mandatory to do internal inspection. So that wouldn't be allowed in certain countries in Europe and around the world. And if really the consequences of failure are particularly high, then you might say, well, that's too much of a risk and we really don't want to take that risk. So you may decide that's not the case as well. Okay, so last sort of slide on the introduction side of things is why some reluctance. Well, it has been a bit of a test really to start on the non-invasive side of things, and that seems to be really because of tradition. Okay, some items are not suitable for an NII, but traditionally open them for proof of process inspection and cleaning, and why would we do anything different? And it's always worth challenging that. You get people that say, well, we've always done it this way, why should we do anything different? So it's worth challenging. It might be that there are unforeseen deterioration mechanisms that might not be detected, and you need some high competence in that. Or some corporations might not be prepared to accept the risk of non-invasive inspection, the amount of corporate rules in that. And also, this is the last point, is some organisations think it's more expensive to do non-invasive inspection because of the additional cost of non-destructive testing. Yes, sometimes there is additional cost of non-destructive testing, but that tends to be outweighed by not having to open and prepare the vessel for entry. And in most cases, that is the case. Yeah. Okay. So, what is the methodology for non-intrusive inspection? So, I'm going to introduce you now to the recommended practice, HOIS RP 103. This is a joint industry project that involves the operators, the NDT providers and vendors, and also the UK regulator, the HSE. And they originally developed this methodology around about 2007, and the latest version of that is now February 2020. So that's another reason I think I wanted to talk about this, because there have been some changes around a more quantified approach. And you can see from the graphic there, it's like a 5-stage approach. You do an integrity review, then a decision process about whether it's viable for non-intrusive inspection. Then you do your planning, then you do your inspection, and then you do your evaluation. Okay. Now, in this, I'm going to really look around the first 3. In a bit more detail. We haven't really got time to go and look at the 4th and 5th. And I think the first 3 are the most important aspects in helping decide. So, the integrity review, really that's about understanding everything about the piece of equipment you're considering for non-invasive inspection. So, looking at the specification, the drawings, its inspection history, has it had any modifications, repairs, any incidents. Some of you might have heard of a process called risk-based inspection, and this is a very good process for understanding all about the equipment and its history and what the risks and damage mechanisms are. So that's a good way of achieving that. You then need to do a corrosion risk assessment. So this is a detailed review of to identify the degradation mechanisms to which it may be subject to. So that could be just plain internal corrosion, but there could be many other: stress corrosion, cracking, hydrogen cracking, dead leg corrosion, all sorts of mechanisms. So you need to review that and make sure you identify all those. You then also need to know about the equipment and what its integrity assessment is. What's its corrosion allowance? Where is it in its life? To what extent can it stand excursions, that sort of thing. And then finally, what's its operational experience? Has it operated with the envelope that it's designed for? Has it had excursions that may have? Is it likely to have further excursions? that may take it outside the envelope where other damage mechanisms come into play. So that's your integrity review. That's about understanding the equipment and what it's subject to and its history and its construction. The next phase then is your screening, your decision process, your screening phase. So in the recommended practice 103, there are these selection charts. The purpose of this first stage is to quickly identify those vessels of which it shouldn't be considered, it's not really viable. And it asks really four basic questions, and that is the vessel intrinsically suitable for non-invasive inspection? What that means is, if you're saying that there's internal corrosion, and you might be able to measure that from outside using ultrasonic thickness testing, then can you access the outside, or has it got some sort of cowl on it or something that prevents that? So you need to assess that. It might have internal components that you can't get access to without going in the vessel. That's the sort of question we're asking there. If you answer no to that, then NII is not viable. Has the vessel previously been inspected, and is the history still relevant? Okay, if you've got no inspection history whatsoever, then it's hard to justify non-intrusive inspection. It might be that you've got similar vessels on similar duty that you can take credit for, in which case that might be possible. But the general rule is if you have no inspection history for that vessel, then you really need to do an invasive inspection first to get that history to verify that what is taking place there. The third one is the operating history still relevant? So do we know what that is? Is that consistent? Is that predictable? Because of course that may likely affect the damage mechanisms that we need to assess and mitigate for. And then finally, is entry scheduled for any other reason? So if it's going to be opened up in a turnaround for cleaning, or maybe a packing replacement or something like that, then you should really do the inspection invasively alongside that. So if you answered it's going to be opened for other reasons, then it would say, well, you should really do invasive inspection. Okay, so that's the first stage screening, and it will take you through to whether it's viable or not, based on those four questions. The next stage is a high-level decision process, and again, it's following a flow chart, and it's asking really three questions next, and that is, what is the confidence in the ability to predict the type and location of degradation? So this is where your corrosion risk assessment comes in, and you have to be clear about, yes, I'm sure that will occur, and it will occur in that location, and that I'm quite happy that we can predict the rate, and we can monitor that with an appropriate non-destructive technology. The next is, how effective was your previous inspection? Because many a time I've seen inspection reports and lots of them saying, yes, we've done inspection, we've done 5 inspections. But when you look at the inspection, it's been very poor. They haven't really looked in the right place, they haven't looked at the right mechanisms, they haven't done the right inspection and testing. So it's really about understanding how effective that inspection was to give you an idea of what the vessel is exposed to, and whether that's okay or not. And then what the severity and rate of degradation is. If it's a very high rate and severe rate of degradation, then that might not really be feasible for an eye. So you answer these, you can see that these are answered sort of medium and low, and that will either give you an eye possible yes or no. Okay, so so the second point is a high level decision process. If you get a yes out of that, then you can go on to the next step. And the next step then is the development of a non-intrusive inspection plan and work scope. So that tends to consist of the definition of the vessel zones. So you do a sketch according to the methodology that helps split the vessel down into various, the liquid side, the vapor side, and the gaseous side. And then where the inspection zones are, that you will look for those different damage mechanisms. And it will also list what the work scope is and what the coverage calculations are for your testing. and then you'll also select your NDT methods. Okay, so that's the third step. And so just coming back to our methodology, you can see now we've done those first three, ticked to those, and the other two I wasn't going to talk in detail about really was to perform the inspection and testing and record results and any non-conformance against the plan. So quite often sometimes inspections don't go to plan and you don't get full coverage of the NDT and such. So you need to record how the inspection's gone, what your findings are, did you do it fully, and then evaluate that against the criteria and the methodology to help decide whether that was acceptable or not. So that's about the inspection and the evaluation of the inspection, and then completing the loop. So that's the methodology of how you would go about carrying out an inspection for that. So we have now our second poll question. I don't know whether that could come up or not.
Dave, the audience can see the poll questions, so just carry on. And they got the answer to the first one. It's just you, me.
Oh, right, okay. Oh, I see. So I'll read that out then. So what do you think the average percentage of vessel inspections could be non-invasive? Now, I don't unfortunately, because I can't see them, I don't unfortunately have that written down, but I think it's something like 0 to 20%, 20 to 30%, 30 to 50, and then over 50%. So if you can put that down, I don't see those results, but you'll see in the later on slide, we've got some case studies there that will help answer that question. Okay, so moving on, we're going to look at some examples of non-destructive testing that helps support non-intrusive inspection. Just in the methodology, there are, in the appendices, there are some tables that help you choose non-destructive testing and whether they are a high, medium or low effectiveness, and what the parameters are for each technique. So very helpful again in the methodology. And by the way, if you just go to that site, you can download this for free as well. You know, you don't have to pay for these documents, so it's very good. Okay, so just a few examples of non-destructive testing. Corrosion mapping. So this is an automated process. So what we're looking here for thinning of the vessel shell wall, and it maps out, losses in material thickness. It's used phased array ultrasonic probes that give multiple scans at high speed and accuracy. Tends to be on this carriage that automatically tracks around the vessel and indexes where it is, and it gives out a pictorial report. So this is like a heat map. You can see the reds are where it's thinner, and you can see the cross sections of where it's thinner in those points as well in both directions. So this is your sort of scan data, your C, B and D scan in terms of non-destructive testing. So very, very effective method. You can scan large areas of vessels automatically and with consistency. So that's corrosion mapping. Another technique coming through now. You can, if it's hot equipment, normally not conventional ultrasonic thickness testing is around 80 degrees centigrade as a maximum, but you can use specialist equipment that can take up to 350 degrees. There are some, I wouldn't say it's common, but it is possible. They use special cooling systems, special couplants, and it's automated so the person doesn't have to go and put the probe on themselves. So that's useful if you want to keep the equipment online, it's on hot duty, that is possible. Another technique, time of flight diffraction, TOF. So what this is really for measuring flaws. This is things like cracks or features in parent metal, and it uses ultrasound, and it's got a transmitter and receiver, and it sends ultrasound, and when it hits the defect, it reflects back, and it can triangulate where that is, and it can size it very accurately, and gives an immediate report of where that is. It's very reliable. It's very reproducible, accuracy within 0.5 millimeter. It gives a permanent digital record, and it's better than the traditional radiographic and manual ultrasound techniques. So you can see there, those are the two transducers, and you just roll it up the weld like that, and that can test the weld, any defects in that weld there. So that's time of flight diffraction, quite a common one, very effective. A couple more. We can do digital online, so real-time erosion and corrosion monitoring. You can put sort of probes on pipes or vessels, and it can talk back to the plant DCS or whatever through these modules by Wi-Fi, and you can online monitor defects. Another one is tank floors. So you can send robots in tank floors now, and that can measure the thickness of the tank floor. I know it's invasive, but it's not having somebody, you don't have to empty it out, and you don't have to prepare it for somebody to go in, so it is an advantage. Another final one, as an example, would be drones. We're starting to see more of these now, and you can put these in these little sort of cages and put them in a tank, and it can fly around the tank or roll around the tank. So that's another way of doing sort of non-invasive inspection. It's invasive, but you're not having to thoroughly clean the tank, or you're not having to prepare it for man-entry. So again, useful information for things that might be hard to detect from the outside. Okay, so just a couple more things now. So when we talked before about examples, we've got some case studies here where on an onshore refinery we did some reviews of 160 vessels, and it turned out that 95 of them were suitable for a non-invasive inspection, so that's 58%. So you can get some quite high percentages that are suitable for an invasive inspection depending on the process duty. And then here's another sort of case study. This is a refinery where we looked at 540 items where they wanted to move the shutdown from a 3 to 4 year period and go non-invasive where they could. And we did that. We eliminated 20% of the work scope of the turnaround, and we moved it to 4 years, and 58% of the equipment was suitable for non-invasive inspection. So we managed to take a lot of the equipment out of the turnaround and do that before the turnaround. So if there were any problems, that could be fixed in the turnaround. So a lot of benefits to be gained from non-invasive inspection in that respect. Okay. So in summary, non-intrusive inspection is becoming increasingly more the norm. It's accepted and tested methodology. The regulators involved and supports this. There are more advancing NDT methods that's helping us do that. Some of those we looked at. And there's a drive, obviously, as we all know, to improve plant uptime and optimise costs. So that's helping drive that. We must, though, these assessments must be carried out by competent and experienced people. So people that are qualified and experienced in inspection and so on. It might not be possible in some countries due to the national rules and regulations. Don't forget about the other benefits of non-invasive inspection, other than cost saving. We saw those. And it will still be required where the criteria is not met, and for instance, where the consequences are very high, and really the risk is not a viable risk for non-invasive inspection strategy. Okay, so that's the end of my presentation. Thank you very much for listening, and I'll take any questions.
Dave, can we take questions right at the end, and we'll move on to the next presentation, and we'll come back to questions. I'm just looking at the time as well. Is that okay?
Yeah, certainly. Yeah.
Okay, so can I invite Praful Sharma to come present the next paper on corrosion radar?
Thank you, Alan. Is my voice audible properly, Alan?
Yep, loud and clear.
That's great. Thank you. Thank you. And thank you for invitation to present the predictive corrosion monitoring technology for corrosion under insulation. My name is Praful Sharma, and I'm excited to present to you some of the latest and greatest on predictive corrosion technology being invented at CorrosionRADAR for various applications, including CUI. So just a brief about myself. I'm the CTO of CorrosionRADAR. Before this, I was in Cranfield University doing my research where this technology was invented, and we'll talk about it a bit. Before that, I spent about a decade in the industry developing various NDT technologies with a company called General Electric, and that's my brief background. So CorrosionRADAR is a spin-out of Cranfield University, as I mentioned, and focused on predictive corrosion monitoring technologies. So today's agenda here is split into a few parts. We'll talk about why we are talking about corrosion or predictive corrosion, and what is the solution we're talking about here. What are the case studies? How do we do ROI? And question and answers in the end. I'm aware of the time, so we will. I'll try to be faster with the good messaging, but we may have to, if the audience is interested, I'm willing to spend more time than the usual time till 6, beyond the stipulated time as well. So very well okay with that. So let's jump into why we are talking about what we're talking about. Is because it's an era of inspection 4.0. Now this is an important slide actually, because that's how I see this, where we are heading towards. And I think some of it is related to what even David talked about in the previous slide. So we talked about, so we hear about a lot about industry 4.0. We hear a lot about digitalization, what it means to inspections. And that's the context I'm trying to say here, that we have probably last 50 years, we have gone from inspection 1.0, where it was manual observation leaks. In some cases, it's still the norm, but we have moved beyond that to inspection 2.0. Somewhere in 1980s, 90s, where entity instruments started to come, measurement started to happen. And then early 2000, people started talking about RBI optimization of the inspection process, because the volume of the pipelines is just too large. That's where we are between 2 and 3, but now industry is starting to move towards inspection 4.0. It's automated, it predictive, it's analytics. And the reason is manual processes are expensive, it's becoming more automated. Detection is becoming prediction, and even we have reactive methods are becoming preventive. So predictive corrosion management is a huge opportunity. So even before corrosion has happened, can we predict and mitigate and even schedule an inspection accordingly? And this can be enabled by industrial IoT, the latest and the greatest in the sensors and wireless and predictive analytics, say statistics to start with, and machine learning as a state of the art. So the reason is current practice is reactive. When you're worried about an equipment, the corrosion might have already happened. And all the technologies right now, say visual inspections or even NDT, they're detecting a metal loss. I understand metal loss, corrosion is an aging process. We can't avoid it. We're trying coatings, etc. But the current methodologies to detect a loss which has already happened. It's like you already get a disease in your body, and you realize it very late to detect that disease. We as human body, we know about a potential onset of a problem very early on. Can we bring the same philosophy to corrosion management? And that brings me to predictive maintenance, which is on the right hand side. You see here inspection 4.0. Can we have sensors doing continuous monitoring with knowledge base models to predict the areas where corrosion might happen, and this will lead to reduced scheduled maintenance, proper scheduled maintenance, improved safety, and reduced cost as well. So it's a huge opportunity for the whole industry. We as Corrosion Radar see the first application of this to be corrosion under insulation, and this is the first strategic target segment for Corrosion Radar, and that's the reason that this is number one. Many times it's said it's among the top asset integrity issue in oil and gas and petrochemicals. Basically, majority of the pipeline failures are due to CUI, documented in the literature. Up to 10% of the overall maintenance, offshore maintenance cost can go to CUI. We have seen high profile cases in the North Sea as well, where production losses has happened, leading to hundreds of millions of dollars loss in the production cost. So how CUI happens, I believe audiences should be well versed with it, but just for sake of completeness, CUI is corrosion under insulation, which happens on the outside surface of the pipelines or equipments, and they are hidden normally because of surrounding insulation. What happens nearly is normally there's an insulation around the pipes or vessels, but this insulation is supposed to be a protective insulation. They're supposed to be good things, but they can turn into devils if they allow water to go in. And invariably, over the decades, industry have realized that it's nearly, if not impossible, it's very difficult to have sealed systems where no vapor goes in or no water ingress happens due to rain or even condensation on the surface. But it does happen. It breaks the coatings. It starts to corrode the pipes and sometimes leaks. The problem is unpredictable location, and because of this uncertainty, industry is spending millions and actually billions of dollars annually to locate proactively where it is. So people open insulations every few years just to find out the conditions of the assets. Can we do better? Yes, we can, and that's where the benefits of CUI monitoring comes into picture. So why CUI monitoring? Because if you have corrosion sensors or moisture sensors, I'll describe them in more details, you can have better RBI. David talked about RBI, risk-based inspections. It's a great tool to prioritize the inspections, to inspect only where you think the consequences or the probabilities are higher. But there is very little information coming from the field, and that's where the sensors comes into picture, that sensors can give information and we can have a better RBI process. Optimized maintenance leading to predictive maintenance, leading to even prevention. If there's no RBI, even you can have early detection to that effect. Before I move forward, I actually missed a point. So can we launch our first poll, please? Which I will read out. The poll is asking, how do you rate the effectiveness of the current approach in your industry for CUI management? Answer 1 is very effective. Answer 2 is somewhat effective. And third one is not very effective. I would like to understand what the audience thinks the problem of CUI in their industries. I know this is particularly problem for oil and gas and petrochemicals, but some of the audience from here can be from that industry, but some of them will be from different industries, and this is the problem is different from different industry. So yeah, so please select the right appropriate answer, and then we will publish the answers as soon as possible. So yeah, so when we have the answers, please can we have the answers published on the screen, please? Right, so we have the answers here. About 7% people think it's very effective, which is minority. About 17 to 56% feel it's somewhat effective.
No,
and
sorry,
11 to 30.
Yeah, it's 56% feel it's somewhat effective. The 17 is the number of people who responded. That's why it's got 17.
All right. Okay. So 6% thinks very effective. 56% majority thinks somewhat effective, and 36% feels not very effective. So So basically, we have a long way to go there. It's very clear that probably more than 90% thinks it's somewhat effective or not very effective. And that's why we are talking about it together. So thanks for that. So what is the solution in that case? Of course, there is no holy grail to that. It's a system problem. CUI is a system problem. It consists of insulation. It consists of coatings, etc. But what we are saying is corrosion radar is it's a predictive corrosion management issue, and it's a part of the puzzle where if you put sensors, at least we know more information, we can manage it better. It's same as human body have got their nervous system to tell them that there is an issue, right? The pipes don't have a nervous system, so can we build sensors effectively like a nervous system to tell that there is a potential problem happening? So the solution Corrosion Radar have developed is the detect, connect, and predict. These are the three pillars of the system. Detect, connect, predict. It's called industrial IoT system, industrial Internet of Things. That's the new era of cheap sensors, wireless connectivity, directly on the cloud, visualization. It's becoming very easy these days. So this system is having, on the detect side is the sensors. There are two sensors, corrosion and moisture. We'll talk about it more. Connect is the electronics, and the predict is the analytics and predictive algorithms. So predictive algorithms are interesting that with say moisture sensors, moisture there, you can have coating risk as a prediction, which is under development right now. The stress corrosion cracking risk. It's not a detection of a stress corrosion cracking, but prediction of stress corrosion cracking, that with water, no water means no, very less risk, but with water the risk suddenly increases, and even corrosion risk. So these are the example of hardware and the analytics which can help in the decision making. So coming back to the hardware, the first part is the sensors. Now here we are showing the sensors, two types of sensors, corrosion and moisture. The sensors are in the form of long range wire or fibers. They are embedded inside the insulation. They're installed typically during an inspection time window when the insulation is getting removed, or during greenfield when the design process and construction is happening. But the orange color shows the sensors, which can be straight length or helical or any other shape or form. Effectively, they're like very flexible. They get installed like a heat tracing system. They go around bends and flanges very similarly. Similarly, there's a mesh configuration as a mat, or goes around specific high-risk areas in the pressure vessels. So to summarize, it's an embedded sensors, long-range, modular, unaffected by complex geometries. Two sensors, corrosion and moisture. Corrosion sensors covers up to 100 meters from one location. So the next question is, okay, fine, these are the sensors, but what is the principle of measurement? So that's the next slide, which is the principle of measurement is an electromagnetic guided radar. So if you have a sensor, it's the longest coupon in the world. The external layer of the sensor is made of carbon steel, so it's kind of sacrificial partially. But when you have the longest coupon in the world, the second question is, in that 100 meters, where that corrosion coupon is getting corroded. So we use radar principle for that, to similar technology which is used in space industry to with microwaves. We send radar signals inside these sensors, which are acting as a waveguide, and we do get reflections which are shown here as a signal on the top of these black pipes to locations where the peaks can be seen. Those kind of signals are received, and with time of flight we can locate where exactly corrosive conditions are getting developed and moisture is getting developed. So again, this is not measuring anything on the pipe, it's measuring predictive. When we say predictive, it is not an NDT technique, it is more of a predictive technique, which means it is before corrosion has happened, it is measuring the corrosive environment, it is risk profiling the assets using corrosion sensors and moisture sensors. So that's the principle of measurement. Electronics is an ATEX certified electronics. You can see the battery here, ATEX certified, and there are various connectivity options, Wi-Fi, cellular, wireless HART, or LoRa. And then the data comes wirelessly to various platforms of choice. The platforms are shown on the top, which is first is the industrial IoT cloud platform, which shows the data. It's a web-based access. The second one is many customers wants the data to be on their premises, so we are we have an on-premises software platform where the data is shown there. The third one is more of a demonstrator we have made with working with some of the 3D digital twin companies which provide this service to the end users. If you have a digital twin, we can provide the data in the format where the assets become color coded towards the risk of the asset. So if it is red, it shows the location where the red is, its risk is high there. And we can move the slider towards future as well because there is a prediction element. So how the colors risk will change in the future. At the bottom, there are various algorithms, so analytics algorithms or prediction modules, be it for corrosion rates from API 581, etc., or be it coating risk, coating life reductions, or stress corrosion cracking risk. So there are various algorithms which can be, which can be activated on each of these platforms. So let's see some case studies. Where have these been deployed? So let's see case study. This is among my favorites because it is a production column. It's a high value asset. So you see the picture. This is located somewhere in Netherlands. This was going through a turnaround, and this has a history of corrosion under insulation on the external surface, of course. And the customers was inspecting this every 5 years for time-based inspections, and they were spending huge amount of cost in scaffolding. So they said, okay, sometimes we do find CUI, sometimes we don't find CUI, so many times it's an unnecessary exercise. Can we move to condition-based inspection rather than time-based inspection? So for that, they need a monitoring technique, and that's what we did exactly. The orange colors here on the schematic shows the sensors on the top and the bottom, and connected via bridge cables, long cables, to the electronics in the middle. The electronics picture is shown transmitting wirelessly through an antenna on a cellular network. And now this asset is getting monitored for moisture and corrosion. So the sensors are looking, these are the pictures of sensors getting installed before the insulation. And then the insulation is reinstated and shiny after that. So the objective here is, if so far we have not detected corrosion on this or even moisture, so looks like the insulation companies have done a very good job. But over time, if water starts to ingress, we will detect it. And at that point, the customers will decide whether this to be inspected in the next few years, early or later. If there's no water ingress, then they will actually postpone the regular time-based inspections to the time when this is to be done, say maybe 10-year cycle. Even if they find something, they will not do, their objective is not to do scaffolding, but do a rope access. Rope access is much cheaper as long as we can precisely locate plus minus few meters, square meter where water is and the corrosive environment is, so that they do an inspection at that. So this can save a lot of cost to them, and that's why this is one of my favorites. Case study B. This is more towards moisture sensors. You can see figure D, which is corrosion and moisture sensor at the bottom. Moisture sensor is placed at the bottom, but it can be placed anywhere. And the data looks very interesting here because if you see, this is the format we show the data, historical. X-axis being the date, or say time or date. Y-axis is the distance along the pipe. And you see at around 22 meters location, we started to see some patterns of rainfall, and it was highly correlated with the rainfall in that region. So water is getting in. Normally it is not supposed to, and that's the precise reason why CUI happens. But there's more information here. One is location of that problem, so customers can actually prioritize the inspection at that location and deprioritize inspection at other locations. And then also the wetting and drying cycles, which are actually one notch higher of corrosion severity, because these coatings does not like this drying and wetting cycles, and this is happening here. So this will be a high risk area. Now case study C, complicated pipe somewhere in Asia. We have corrosion and moisture sensors along this complex pipe network, and let's see how the results are. So after 9 months of the data collection, after the sensors are installed and the insulation is put back, we do see corrosive environment at the top and lowest points, and also moisture water getting ingressed at multiple points. Looks like the insulation company have not done a good job there. The assumption is invalidated. Normally, the assumptions of the operators are that the insulation companies are following the guidelines, so everything is perfect. But because of those imperfections, water is going in and leading to asset integrity issues. And this is precisely what monitoring techniques can do about post-inspection assurance as well. So this brings me to the poll number 2. Can we launch poll number 2 on the screen, please? Because we are reaching on the last part of my presentation, and also we are slightly delayed. So I think we will spend probably 4 or 5 minutes after 6 o'clock to handle question answers, or even 10 minutes if people are around. So the poll is, which of the following can improve the management of CUI in your industry? First is prevention. Continue with coatings and insulations, because that's been the norm. We have been using them. Second is detection. Increased manual inspections and NDT. Maybe we are not doing enough, but probably increase frequency of NDT and doing more. And the third one is prediction. Adopt digital analytics and continuous monitoring. So I want to understand your views of what your views are. And once the time is up, I think we'll publish the results online and see. I'm very curious to know what your views are. As in the past, you have mentioned that CUI is not very effectively managed right now. So what is the best way? So yeah, whenever the time is up, let's see the results. While we are getting the results, Alan, do you think we can extend this by 10 minutes?
I think we can. I'm just wondering if you just move on to the next slide, and then as the results come on, you can just go back to the results, because it takes
all right,
some time to come up with them.
Sounds good. Okay, so this section is about pilots, and how do we, if you are interested, how do we do this? How do we use this technique? So normally we do pilots or on various assets. So this gives an idea. This slide gives an idea of what kind of assets are useful. Normally we select all of them or some of them, depending on availability. So the asset number 1 is a small pipe, 2 is large pipe, 3 is a horizontal vessel, 4 is vertical vessel, again pressure vessels or even production columns. The one I showed is 25 meters high. So you can select them, and then we can discuss to do pilots. Even large scale deployments can be discussed. So that's how we select the pilots. Now the poll results are out, and prevention got 23%. I think it's a mixed result. So prevention, which is normally the best, we need prevention actually. No CUI is the best. Prevention is better than cure. So coatings and insulations, that got about 23%. Detection, which means increased NDT, is 21%. Prediction is 23%. That's a very interesting result, because normally people tend to think that prevention is the best way, but in this case, coatings and insulations have failed us in many ways. We are still waiting for the best ideal coatings and insulations. Till that time, we need. I agree with this, that we need to continue, have more analytics and more digital techniques also being thrown into the mix. But we have to coexist with all of them. There's no silver bullet. All the process, all the things needs to be used. So that's a great poll result. So coming back to our slides, normally when you are looking at digital corrosion monitoring, the first question management asks is what is the cost benefit analysis? What is the return on investments? And this is important to do. So we do this as part of the procedure. After you select the asset, we sit down with the asset owner and really find out what is the cost of inspections over a life cycle. So we have various inputs, how many years of cycles, and in which year, how much percentage of inspections based on their procedures, and how much that can be reduced with monitoring. Can we do surgical inspections when only where it is required? Can we avoid inspections when it is not needed? So the whole optimization process can lead to a lot of cost savings, and that's the output of this workout during and before the pilot. So we have done in the past for offshore as well as onshore assets. for depending on the asset type, the cost savings can be anywhere from 30 to say even 50%. And there are of course better risk management here because of the data. What I have not talked about is the RBI, the enhancements of the reliability of the RBI processes as well. So this summarizes the last slide of my presentation is predictive CUI monitoring. Key takeaways this is predictive. This is not detection. This is prediction, which means the philosophy is a bit different. It is geared around finding the conditions of corrosion and not the corrosion itself. So this is much earlier, which gives a lot of benefits. So predictive CUI monitoring, cost benefit analysis, and ROI calculations are very attractive. Pilots to scale up. We can. I mean, we'll be happy to discuss. Again, digitalization. This is under that remit. There are many organizations which are going through digitalization drive, and this fits very well. Again, dedicated seminar for your organizations, and there are various business models. There are various methods which are coming up. Rather than hardware sales, people are deploying as an operational model as well, which is data as a service. So they deploy as a at a low cost hardware, but it's like mobile phone subscription charge that you deploy it but pay over time based on the amount you use, the data you use. So these are the new business models which are coming up in the industrial IoT. So I hope this was useful, and you can contact us at info@corrosionradar.com if you are more interested in knowing more about it. And I'm open to question and answers. Sorry, got extended in time a bit, but happy to take some answers, and David as well. So I think we will take joint questions and answers. Thank you.
Okay, thanks very much, Praful, and thanks, David, as well for the presentation. So I've got a number of questions here, which let's get through those questions. I think the first two or three are for you, Dave. So the first one is, what's the difference between NII and NDT? That's from Andy Batters.
Okay, NII is non-intrusive inspection, so that's doing inspection from outside the vessel. NDT is non-destructive testing, so that's the testing methods that you saw some examples that you would use to support non-intrusive inspection. Hope that's clear.
Okay, and the second one again for yourself, Dave, and is, could you please comment on the links between NII and RBI? Examples of the same inspection effectiveness or confidence, e.g. API 581 level B, can be achieved by interval visual and NII for general corrosion damage mechanisms, but localized corrosion mechanisms require extensive corrosion to achieve the same effectiveness. This means the inspection costs end up being a lot more, but may be justified on the basis of avoided production losses and mechanical costs to prepare equipment for entry into an internal inspection. Did you pick all that?
Yeah, I'm not sure I can answer it, but yes, obviously if there's a corrosion mechanism that is particularly aggressive and not predictable, then the process, whether it's risk-based inspection to 581 or NII to the recommended practice I showed, that may define extensive coverage of non-destructive testing from the outside, and that's really where you need to compare the benefit that you will get, because you might find that it's a very large vessel and you've got to scan the whole external because because the process says that, then it might not be the best method to go forward, really. So in a way, that's part of your assessment. Even though it might be safe to do so, you need to look at the economics of that as well. So hopefully that answers that. Okay,
thanks, David. For a full one for yourself. So since the CUI, the corrosion sensors are themselves measuring corrosion, so how is it predictive? It also seems to be reactive.
That's a very good question. I think I believe this is still predictive, because the corrosion which is being detected by the sensors are on themselves. They are coupons, so to say, and they detect the corrosion at a very early phase. Say, for example, if corrosion rate is about 0.1 millimeter per year, which is very low corrosion rate, this corrosion is detected within 6 months. Normally, people will not even notice this level of corrosion, right? But even after a year or two. So it's very early detection from the corrosion sensor, but when it's moisture sensor, it's really when the corrosion has even not progressed much, because of coatings, corrosion might not have happened unless coatings are damaged. This becomes a predictive method with moisture sensor. So the whole philosophy is predictive. That can be detect early and even predict with by measuring conditions around the asset. So yes, it is self-destruct corrosion coupons, but very early detection. Yeah, Alan.
Okay. Yeah. Okay. Thanks. All right. I need to read this out to work out which one this is for you. It's a long question. Generally, every equipment, piping and pipeline has an inspection frequency. The time of inspection interval for insulated assets. Insulation will be required to remove definitely. In that case, we can visualize the asset CUI condition. In this scenario, how do you think the monitoring of CUI should be implemented as an additional predictive measure? That's for you, Professor.
So if I understand the question correctly, if it's asking that the insulation needs to be removed anyway for inspections, so how monitoring can help, is that the good summary of it?
I think that's the summary of it.
If that is the case, so the whole objective is to not to do unnecessary inspections. If water is not there, corrosive condition is not there, not to do any inspections. But if it is there, where to do inspections rather than blindly. So basically move away from blind time-based inspections to very informed, targeted laser condition-based inspections. And that's where monitoring fits into it. Inspection is needed, but pre-screening tool like this can tell where and when to do inspections. So this is not getting away with inspections. This is just complementing it and making inspections more smarter, I would say.
Okay. Two more questions, and then I think we'll finish for today. It's one for each of you. And the first one's for you, Dave, another difficult one. Can NII be applied to underground buried or mounted pressure vessels, i.e. access to external surfaces is restricted?
Yes, it can. In fact, we've just been looking at a case, natural gas filter that's buried, and you can look at it through, there's various NDT techniques, radar techniques, but also looking at things like the cathodic protection system to see if there's any sort of indications of corrosion going on there. So if you don't see any indications of corrosion, you might do some sample excavation to confirm the absence. But other than that, you'd be okay. Now, from an internal point of view, if you can suggest that there are no active damage mechanisms, for instance, it's national transmission gas with no moisture, then you can actively take credit for that, having seen it previously, no progress, then you can again say, well, I don't really need to go in that.
Okay. Dave, given the time, I'll take your answer as yes. And the actual user is gas. What I'll do is I'll just connect you two up together, and if he's got any more questions, he can post them directly to yourself on that one. Okay, if that's okay with you.
Okay. Yeah. Case by case basis, I'm afraid. Yeah.
Right. Praful, last question for yourself before we finish. Does corrosion radar also help predict the possible failure of welded joints?
Well, I mean, there are two sensors. I would say we have to see it in this context that if the failure mechanism is affected by water, then detection of water is a good indicator of the risk. So if welded joints are getting affected by any of the conditions which, the materials being used and the conditions are being used affected by water presence, then yes. Otherwise, it's a difficult, probably we need a different sensor. Similarly, for corrosion sensors are made of external layer being carbon steel, so they get affected by chlorides, and if there's an attack of chlorides or any of the acid attack on any of the welded joints, corrosion sensors, if they are placed in that location, will pick up that there's a corrosive environment there. So the answer is case by case again. If the conditions are because of water or chlorides or any such which are detrimental to carbon steel as well, the welded joints, then it is applicable. Otherwise, we have to look for better, applicable techniques.
Okay. All right. Thank you very much. Can I just take this opportunity to thank both speakers, David Burgess and Dr. Praful Sharma. They've both taken time after work to first prepare their presentations and deliver two excellent presentations. I think we've answered most of the questions. There's been a handful of questions we haven't answered. I'll try and get those from the IMechE, and we'll try and answer those separately as a result of this. And thanks everyone for coming along to this. Apologies we overran by 10 to 15 minutes, but I found this very, very interesting, so I didn't want to put off either of the speakers. And hope you all enjoyed it, and dial into the next IMechE Tech Talk. Thank you everyone, and please stay safe, and hope everything goes well. And thanks to the two speakers.
Thank you, IMechE. Thank you, Alan. And thank you, everyone.
Yeah.
Bye.
Thank you, everyone. Yeah. Bye.